The normal curve. The normal curve is often just called the bell curve. It's a statistical theory that says if we look at a population with enough data points, that the results will fall into this natural pattern with some low scores, some high scores, but most scores right in the middle. IQ is one of the examples we could use with the bell curve. If we look at the IQ of the American or the world population, we know that some people have a low IQ, some people have a very high IQ, but most of us just are somewhere around the middle. We can also think of things like standardized exams or the SAT scores. Some people are going to score low, some people will score high, but most of us are going to score somewhere around the middle. Graphs of normally distributed data are usually bell-shaped curves. This is because when you look at the entire population, more people fall in the middle than on each end. This can be used when describing large data sets such as IQ scores, heights and weights, standardized test scores, populations, how much babies weigh, how long fishes are, measures of reading ability, etc. Now the exact shape of the normal curve depends on the mean and the standard deviation of the particular data set. If we change the standard deviation, then that changes the steepness or the flatness of the curve, but it doesn't affect what's in the center or the mean. If the standard deviation increases, the curve becomes wider and flatter. If the standard deviation decreases, it becomes steeper and taller. Characteristics of the normal curve. A normal curve is smooth. It's basically shaped like a bell or a mountain. It's symmetric about the mean, and the mean falls right smack at the peak of the mountain or the top or the middle of the data range. If you fold the normal curve in half, it should basically match side to side. It's symmetric. The tails are asymptotic. Remember our graphs in Algebra 2 where we talked about asymptotes? This is the same idea. The tails of the curve get closer and closer to that bottom line, which is really just a measuring ruler, but it never touches and never crosses. The mean, the median, the mode, and the mid-range are all the same number and occur right in the middle of the hump of the graph. Look at these 9 curves. Which of these are normal curves? If they aren't normal, then which of the characteristics do they not have? The 68, 95, 99 rule. Approximately 68%, or about 2/3 of the data, will always fall within one standard deviation of the mean. Looking at the picture, this is the red area. That middle line is the mean value. So if we were measuring the length of fishes and the average length was 12 inches, 12 would be marked right on that vertical black line in the middle of the curve. The two red areas are 34% below and 34% above the mean, and that's where the bulk of the data falls. Approximately 95% of the data falls within 2 standard deviations, so plus or minus a standard deviation twice from the mean. This includes the red and green areas together. Approximately 99% of the data falls within 3 standard deviations of the mean. So if we look at the red, green, and blue areas together, this only leaves 1% of the data measurements to be shared in the 2 tails designated as white in the picture below. Properties of the normal curve. When students take standardized tests, they're often scored in percentile. A percentile shows what percent of the scores fell below your score. So for example, if you score at the 84th percentile, as in this picture, that means 84% of those taking the test scored lower than you did. Where does the 50% come from? And where does the 34% come from? That together make up the 84% to the left of your score. Properties, again, your percentile score tells the percent of people scoring below you. The highest possible percentile is 99 percentile. Why is this? 50% of the data falls below the mean and 50% falls above the mean. And the total area under the curve is 1 or 100%. Drawing and labeling the normal curve for a specific problem or data set. First, we draw a normal curve, as here. We place the 7 blue vertical lines to designate the standard deviation measurements. We label the center vertical line with the mean value at the bottom. That ends up being here. And then we label each of the other vertical lines by iteratively adding or subtracting the standard deviation. So this line becomes the mean plus a standard deviation, a mean plus 2 standard deviations, a mean plus 3 standard deviations, and opposite on the other side, the mean subtract 1 standard deviation, subtract 2, subtract 3. This labels the curve, and then you're ready to actually examine and analyze the data. Raw scores by themselves don't have much to tell us. If I tell you I got a 20 on my quiz, that really doesn't tell you how I did unless you knew how many points were possible. This is what we use for a z-score, and then we can get percentiles from there. We can't compare scores between two tests unless we know something about the mean and standard deviation on both tests. So we turn our raw score, my 20 points, into a standardized score called the z-score. I do this by taking my raw score 20, that's the x in the formula below, subtracting the mean from it, and then dividing by the standard deviation. This really tells us the distance from the mean, or how far from normal my score is. If my score is very high, then it will be away from the mean in the positive direction. If it's low, then it will be away from the mean in the negative position. And if I have an average score, then it's going to be really close to the mean. Dividing by the standard deviation allows us to put a measurement on the width of the data set and how clumped together or spread out it is. After you find your z-score, you can look up the percentile on a z-score chart. Here's one example. There's many versions. This one only goes to 1 decimal place. So when you compute your z-score, round it to 1 place, and then look up on the z-score to find the associated percentile. Now, looking at your normal curve graph, you should be able to guesstimate both the z-score and the percentile by examining where your score falls on that graph. If you're slightly above the middle mean line, then you would expect your z-score to be slightly positive, but less than 1, because 1 is going to be at mean plus standard deviation. You would also expect your percentile to be just over 50% percentile. Let's do an example. Draw and label a normal curve for IQ scores. For IQ, the mean is 100 and the standard deviation is 15. So label the picture below on your paper and put in the mean and the other 6 measurements, plus or minus iteratively the standard deviations. And now we're ready to answer the following questions. What percent of people have an IQ below 90? Gifted and talented programs often require an IQ of 130. What's the percentile for an IQ of 130? On the other end, special education programs often use 70 points for IQ. What is the percentile for an IQ of 70? And last, if your IQ is 118, what percent of the population score below you? We can compare scores on 2 exams that aren't equally measured. They may have different total points or different weighting. If a student gets a 20 on a quiz with mean 16 and standard deviation 2.2, did they do better or worse than another student who got a quiz score in another class of 52 with mean 48 and standard deviation 3.1? Well, we can see that both students did better than the mean, but just how did they do in contrast? One way to compare these is to translate each score into their z-score. Use the graphs below and draw and label a normal curve for each quiz, find the z-score and the percentile for each student's score, and then decide which student did better overall. If you've ever wondered what score you might have got on the ACT after taking an SAT or vice versa, this would be one way of saying, well, I would have gotten a such and such score on the SAT if I had taken it.